In this video, we're going to look at the double and half angle identities. In the last video, we looked at what we call the compound angle identities, or the addition formulae. They were sine of a plus or minus b, cos of a plus or minus b, and tan of a plus or minus b. In these cases, a and b were two different angles. When the angles are the same, that is b is equal to a, we have what's called the double angle identities. We have sine of 2a, cos of 2a, and tan of 2a. These are important results, especially when it comes to solving equations and dealing with calculus. Let's start off with the sine of 2a. So we'll take now the sine of 2a. If we use the addition formulae or the compound angle identities, we could write this now as the sine of a plus a. So let's go ahead now and write this out. So the sine of a plus a, using our compound angle identity, would give us now the sine of a multiplied by the cos of a plus the cos of a multiplied by the sine of a. If you're unsure about that, please review the video prior to this one. As we can see here now, we've got the sine of 2a, so we've got sine of 2a is simply going to be sine of a cos of a plus cos of a sine of a. These two things are the same, therefore this is going to now give us 2 sine a cos a, and this is an important result that we're going to use time and time again. So sine 2a is 2 sine a cos a. Let's now look at the cos of 2a. So what we'll do, write it just here, we've got cos of 2a. If we think about cos of 2a, that's simply given to be now cos of a plus a. So using the addition formulae, we can say that the cos of a plus a will be equal now to cos a multiplied by cos a, and then minus now sine a multiplied by sine a. So from here we can see that cos of 2a is going to be cos squared a minus sine squared a. So we can write this in as a result, cos squared a minus sine squared a. So that's now one way the cosine of 2a can be written, and that is something that you need to be comfortable with. We know that cos squared a plus sine squared a is equal to 1. Therefore, there's some variations on this that can prove really quite helpful. So let's look at the others. Let's now take the cos of 2a. So if I just write over here, we know, and I'll write it here, I'll just write cos squared a plus sine squared a is equal to 1. This is an identity that we've seen time and time again. Therefore, I can write just here that cos squared a is actually 1 minus sine squared a, and then we've got minus sine squared a, which gives us the second result that cos 2a is 1 minus 2 sine squared a. So that's now our second result. This is the first one, this is the second one, and there is a third one by simply manipulating this identity again. So this time we're going to switch the sine squared a into 1 minus cos squared a. So we got cos squared a, then minus the quantity 1 minus cos squared a. So this is now going to give me cos squared a minus cos squared a, which is 2 cos squared a minus 1. And that now is the third. Clearly these are interchangeable, these aren't set in stone, but this is 1, 2 and 3. These are just now 3 results that we can see from the cosine of 2a. When I said sometimes it was easier to switch one into sine or cosine, we can have a quick look at that. So say for example I had an equation to solve and I was asked to solve now cos 2a. Let's go cos 2a and then we'll do minus sine a, and we'll let this be equal to 1, and we'll say now that a is going to be between 0, we'll go from 0 to 360 degrees. So nice straightforward interval. Now what we've got here, let's just tidy that up a little. We've got now cos of 2a and then we've got sine of a. This right here needs to be changed. We want one trig ratio. So if I look, I've got sine a, and this is to the first power. So what I could do instead is turn all of this into an equation involving sine a only. So if I look at cos 2a, if I go back to this one here, I can write that this is actually 1 minus 2 sine squared a minus our existing sine a, and that's going to be equal to 1. We can see that the 1's cancel off, and we can just factor this now. So if I take it over to the right hand side, we're going to have now a common factor of sine A, and that's going to leave me sine A, and then we're going to have 2 sine A, and then we'll have now plus 1. So all I look to do is go ahead and solve for that. So we can see that sine A would be equal to 0, which is nice and straightforward to solve, and then 2 sine A plus 1 is equal to 0. So let's just find the solutions of those. I said we're interested in A between 0 and 360. So if we look now, let's draw the sine curve. The sine curve comes round to a maximum, down to a minimum, and then back to 360. So we can see if sine A is equal to 0, let's look at those. Sine A is equal to 0, therefore we can say that A will be equal to 0. We're going to have now 180, and we've got 360 degrees. So 0, and then we've got the 180, and we've got the 360. If we look now, we've got the 2 sine A plus 1 is equal to 0, so we could say that sine A was equal to minus 1/2. Therefore, if we just consider, we're going to have 1 just here and 1 just here. This one will be 30 degrees on from 180, which is going to give me now 210, and then this one will be 30 back, which will give me 330. So we can say that A would be 210 and then 330, and all of those given in degrees. So that shows how we could use now different variations of cos 2A to solve equations. As you go on later with your work with calculus, you will see now some of the huge advantages of writing these now as multiple angles. So cos 2A we could write now as 2 cos squared A minus 1, and then rearrange to integrate tricky functions. Okay, so that's a brief example of how we could use that. Let's move on to tan. So what we've got then is tan of 2A. Let's do the tan of 2A. So let's write this here, tan of 2A. So what we know is that this would be equal to the tan of A plus A. So let's deal with this then. If we look now at the tan of 2A, and I'll write it just here, let's write out tan of A plus A. Using our compound angle identities, we can say that this would be tan A plus tan A, and then we would have this now over 1 minus tan A multiplied now by tan A. So if we look now, tidying this up, we can say that tan of 2A will be equal now to 2 tan A over now 1 minus tan squared A. All we've done is taken now B to be equal to A. Usually if we had the tan of A plus B, it would be tan of A plus tan of B over 1 minus tan A tan B. We've just switched this up and written it now in terms of A. So there are 3 different double angle identities. We've got tan 2A, cos 2A, and sine 2A. As stated earlier, these are hugely important for calculus. One of the main reasons is, for example, if we have cos squared A, we could write this now as 1/2 the quantity 1 plus cos 2A. And I'll let you have a think on how that's done. If we had now sine squared A, we would have 1/2 the quantity 1 minus cos 2A. When we come to integrating, we'll see that we can't directly integrate these with the skills that we have. Therefore, we can write these now like so, and the integration is a lot easier. Let's move on now to some basic work with these double angle identities. Let's start off with a nice example. Let's say sine theta is equal to, let's go for 3/5. We'll say now that theta is an acute angle, so theta is acute, and we might want to find, let's put some on, let's do sine now of 2 theta. Let's do cos of 2 theta. Let's do sine of 4 theta. Okay, sine of 4 theta, and then we'll finish now with tan of 2 theta. So we're told this is an acute angle, so one way that we could look at this is a basic sketch of a right angle triangle. So if we think now we've got a right angle triangle, it's an acute angle, so sine is going to be 3/5, so let's put theta just here. That's going to be 3, that's going to be 5. The sine of an angle is the opposite over hypotenuse. This is a little right angle triangle, 3, 4, 5, Pythagorean triple. So these are all acute, so we've got now sine theta is going to be equal to 3/5. we've got cos theta, which is the adjacent over hypotenuse, 4 over 5, and then we've got tan theta. So tan theta is going to be the opposite over the adjacent, which is 3 over 4. So let's deal now with sine of 2 theta. We know that the sine of 2 theta is 2 sine theta cos theta. So that's now one of the double angles that we learnt. So if we do that now, and I'll write it just here, let's write out number 1. We're going to have 2, the sine of theta is 3/5, and then we've got now the cos of theta, which is 4/5. So that's going to give me now on here, we've got 24 over 25. So 24 over 25 now is the sine of 2 theta. So all I've done is simply plug these in. Okay, now if we look at this one, we've got cos of 2 theta. I've got 3 choices: cos squared theta minus sine squared theta. We've got 2 cos squared theta minus 1, or 1 minus 2 sine squared theta. Now, I've found the value of cos theta. That might be wrong. I'm pretty sure that it isn't, but it might be wrong. Therefore, I'm going to work with the information I was given in the question, and I'm going to write one way that cos 2 theta can be written is 1 minus 2 sine squared theta. So if we look now at the second one, we've got 1 minus 2 lots now of the sine, and we're going to square that. So that's going to give me now 9 over 25. So if I square that, I get 9 over 25. So we've got now 1 minus 18 over 25, which is going to give me now 7 over 25. Okay, so that's now the cos of 2 theta done. What about this one here, sine of 4 theta? Well, this time, if we think about it now, we've doubled this angle up. Therefore, we could write this as 2 sine of 2 theta cos of 2 theta. So all we've done is doubled the angle up here. If you want another way of looking at that, we can look now and say that 4 theta would be equal to 2a. So if we write that now, we can say 4 theta is going to be equal to 2a. Therefore, from this, we can see now that a is going to be equal to 2 theta. So a would be equal to 2 theta. This is a slightly long-winded way around this. So what we could say then is sine of 2a would be equal now to 2 sine of a, which we know, cos of a. So just substituting these in, we can say that the sine of 4 theta would be 2 sine of 2 theta cos of 2 theta. Again, it's a very long-winded way around it, but if you're unsure, that gives us some idea. So let's go ahead and do that then. So what we've got then for part 3, we've got sine of 4 theta. Now we've just found these values. Remember, this here, the one we just found, that's sine 2 theta, that's cos 2 theta. So we'd end up now with 2 lots of sine of 2 theta, which is 24 over 25, multiplied by the cos of 2 theta, which we found to be 7 over 25. So let's go ahead and just plug that in a calculator. What are we going to have? We're going to have 2 times by 24 times by 7, and then over 25 times 25, which is 625, and that gives us 336 over 625. So let's write that there, 336 over 625. Okay, what about tan 2 theta? Well, we know now we can write this as 2 tan theta over 1 minus tan squared theta. We know that tan theta is 3/4, so we can simply sub this in. So let's go ahead and do that. We've got 2 lots now of 3 over 4. So 2 lots of 3/4, and then we're going to divide that by now 1 minus 3/4 squared, which is going to be 9 over 16. So what do we end up with? We could do this manually, or we could just work this out. We've got now 6 over 4, which I could put into 16ths. What's that going to be? 24 over 16. And then on here, we've got now, what am I going to have? 7 over 16. So just working this out in my head a little, which will give me 24 over 7. Do check that. That's my dodgy fractions there. So let's do 2 times 0.75, and then we will divide that now by 1 minus now 9 over 16, and that should give us the answer. Let's have a look at that. So 25/7. So that now is tan of 2 theta. Let's now move on to look at something slightly different. We can use the double angle identities for less obvious cases. So we might be asked, for example, to prove that sine, let's say that sine of 3a was equal to 3 sine a and then minus 4 sine cubed a. Now, there are lots of different ways in maths that you can do that. The way we'd be expected to do it, given the knowledge that we've got, is to write this now as sine of 2a plus a. So this time now we're using the double angle identity and essentially now the addition formula. So if I wrote this out, I'd have now sine of 2a cos of a plus now cos of 2a, and then I'd have sine of a. So what I now need to use is some of my known double angles on this. So let's write this out. Sine of 2a is 2 sine a cos a, and then I'm going to multiply this by cos a. And I'll do this step by step. In an exam, you would be able to just work through this with slightly less steps, but I want to show now exactly how we're going to do this. If we look at this, this has no cosines in it. Therefore, when I've got cos 2a, the choice is now either cos squared a minus sine squared a, 2 cos squared a minus 1, or 1 minus 2 sine squared a. It would seem logical now that I choose the 1 minus 2 sine squared a and multiply that by the existing sine a. What I've got here is cos squared a, so I can write this now as 2 sine a, and then I've got cos squared a. And at this stage you could have just made a substitution. I want to show it step by step. Then we're going to have plus sine a, and then minus 2 sine cubed a. So that's just expanding that bracket there. We know that cos squared a is 1 minus sine squared a, so we've got 2 sine a multiplied by 1 minus sine squared a. That's just using cos squared a plus sine squared a is equal to 1. Plus now the sine a minus 2 sine cubed a. So let's go ahead and multiply this out. We've got 2 sine a and then minus 2 sine cubed a plus the sine a and then minus the 2 sine cubed a. So we end up now with our 3 sine a, so let's write 3 sine a minus the 4 sine cubed a as required. So in an exam you wouldn't do all of these steps necessarily, and there are alternative and quicker ways to do this if you understand work beyond this particular level. But in terms of doing it with this, what we have, this would be one way to show it. So that's a typical example of an identity. Sometimes we might simply be asked to take an expression and simplify. So let's look at some of those. Let's say we were asked now to simplify and evaluate 2 sine of, let's go for pi by 12. So 2 sine of pi by 12, and then we got cos of pi by 12. So in these particular exercises, it's often a case of just spotting the format. Now this looks like 2 sine a cos a. So if I write this out, if I write now 2 sine a cos a, I know that that's going to be the sine of 2a. So if we look here, we've got that a is equal to pi by 12. Therefore 2a would give me now pi by 6. So if I think I've got now my a in this particular format here, therefore I can just simply write this is going to be the sine of 2a. So straight in here we got the sine of pi by 6. Pi by 6 is 30 degrees, sine of 30 degrees is 1/2. So we've evaluated that using now the double angle identity. I've spotted the form, I've subbed it in and looked and compared and just written now that this is going to be sine of double the angle here. Let's say we were given another one. Let's say we were given 2 cos squared, and then we had now 22.5 minus 1. So what does this look like? Well, that looks like now cos of 2a. So cos of 2a can be written in 3 different ways. One of them is 2 cos squared a minus 1. So if we look in this case, we've got that a is going to be equal to 22.5 degrees, and let's just clarify that that is degrees. So therefore 2a, doubling this up, is going to be 45 degrees. So if I look now, I can simply sub this into here, and I can say that this is the cos of 2a, which is a cos of 45 degrees, which is going to give me 1 over root 2, or if we like, root 2 over 2, if we rationalise it. So we've just used now the double angle identities to evaluate. Let's look at another one. Let's say we had now the square root of 1 plus, and then we had, let's go for cos, and we'll go cos of 8 theta. Okay, so what does this look like? Well, we could write again, looking at our double angle identities, we could write that cos of 2a is equal to now 2 cos squared a minus 1. Okay, so let's see what I could do with this. If I add 1 to both sides now, I've got cos 2a plus 1 is equal to 2 cos squared a. Now in this particular case, I've got 8 theta. So if I wrote this out, I could write that cos of 8 theta plus 1 would be equal now, if we just consider this is half the angle, we could write this as 2 cos squared now of 4 theta. So all I've done is simply halved the angle. So we've got the square root, so what we need to do is square root both sides. So I can look at this and say, well, that's going to be cos of 8 theta, let's put 8 theta, plus 1 is equal now to the square root of 2 cos squared 4 theta. So let's write cos squared 4 theta. Just rearranging this into what we had is exactly the same. 1 plus now cos 8 theta rooted is going to be now root 2 cos 4 theta. And that's one of the ways that that can be written. Just one, but it gives us some idea on how we can use now the double angle identities. Okay, let's write another one. Let's go for let's write this one out. Let's go for 2 tan of 5 theta over now 1 minus tan squared of 5 theta. So quite clearly this is something to do with tan. We know now that the tan of 2a can be written as 2 tan a over now 1 minus tan squared a. So in this particular case, we can see that a is equal to 5 theta. Therefore, all we need to do is write that that's going to be double. We want 2a, so we can say that that would be tan of 10 theta. And that is fairly straightforward once you look now at the definition of tan 2a. You are just spotting that you've got a here, therefore you'd end up with 2a. So that's basically evaluating. So we've looked at these, I've evaluated a couple of them with values, and then I've written others in terms of theta. Sometimes we might be asked to prove identities. So let's go ahead and look at some identities. Let's say we were asked to show that sine of 2 theta now, so setting up the identity was now, let's go for 2 tan theta over now 1 plus tan squared theta. Now this is not here tan of 2 theta because we've got now the plus. If it was tan of 2 theta, we'd have a minus. The way I like to think about this now is, what am I aiming to do? Well, I know that sine of 2 theta could be written as 2 sine theta cos theta. So if I can make the more complicated side, which seems the right hand side, look like that, then I can simply prove this identity. So we've looked at proving identities before, and it's a case now of dealing often with the more complicated side and working from there. So let's work with this more complicated side, and I'm going to write now tan in terms of sines and cosines. So what we've got then is 2 sine theta over cos theta in the numerator. And then I've got now 1 plus sine squared theta over cos squared theta. What I'm going to do here to clear this fraction is multiply top and bottom by cos squared theta. So if I multiply top and bottom by cos squared theta, so multiplying the numerator, multiplying the denominator, the numerator will become 2 sine theta. Now the cos squared theta and cos theta will cancel to leave me cos theta. Then I'm going to have here cos squared theta plus sine squared theta. Now we know that cos squared theta plus sine squared theta is equal now to 1. Therefore we can simply sub that in, and we're left now, just telling the examiner what I'm doing here, I've got now 2 sine theta cos theta over 1, and we end up quite clearly with 2 sine theta cos theta, and we can say that sine 2 theta now is given to be 2 sine theta cos theta. So that's a nice way of doing it, and that's one. There are different ways that you could show that, but essentially I'm saying to myself, what am I shooting for? Well, if I can get an expression now such as 2 sine theta cos theta, I know that's sine 2 theta. I've done that by looking at this in terms of sines and cosines and going from there. You certainly don't have to do it that way, but it is one particular option. Okay, let's look at another one. Let's look at something slightly trickier. Let's choose now tan theta. Let's go for tan theta. So tan theta plus now cot theta, and we'll now show that this will be the same as 2 cosec 2 theta. Let's deal with this, 2 cosec 2 theta. When I think about this, this is saying now that this is 2 lots of 1 over sine 2 theta, which is the same as saying now, and I'll write it out here, sine of 2 theta, which is going to give me 2 lots now of 1 over 2 sine theta cos theta, which I could write now as simply 1 over sine theta cos theta, with those 2's cancelling. So if we look at this now, we could aim to make now the left hand side look like that. So that's what I'm going to have, and I'm going to deal with this side. The reason I'm dealing with the left hand side now is that we have an addition between them, which means I've got slightly more scope to work. So if I write now tan theta as sine theta over cos theta, plus cot theta, which we've met before, which is cos theta over now sine theta. Adding these fractions, we need a common denominator, which is going to be sine theta cos theta. And then I consider now what I need to multiply this fraction by. And that's clearly either sine theta, which is going to give me sine squared theta. What do I need to multiply this one by? The answer is a cos theta, which gives me cos squared theta. And you can see exactly where this is going. And again, we would write to the examiner that sine squared theta plus cos squared theta is equal to 1. Therefore, we've got 1 over sine theta cos theta, and you can see now that these are the same, and it's entirely up to you how you want to set that up. You might want to do this now step by step, left hand side, and making the 2 things look the same, or you could simply say that this is going to now be 2 cosec, so let's write this out, 2 cosec 2 theta is going to be 1 over sine theta cos theta. So entirely up to you on how you want to execute that at the end, but essentially you can see how that's working by simply playing with sines and cosines and adding fractions. We might be asked to eliminate a parameter, so let's look at parametric equations. Now parametric equations are x and y, but they're defined in terms of functions of theta or t. So if we were asked to eliminate the parameters, so let's look at some parametric equations. So x is equal to cos 2t. So x is a function of t, and then we've got y as a different function of t. So y is equal to cos t. And we were asked to eliminate the parameter. T is a parameter, or you're asked to simply now express y in terms of x or x in terms of y. If we consider what we've got, then what we want to do is get rid of t. So if I look, I've got y is equal to cos t and x is equal to cos 2t. I can write now a double angle identity for this to now express this in terms of y. So what we could write then, looking at this, I could write that this is 2 cos squared t minus 1. Now we know that y is equal to cos t, so we could write that x is equal to 2, and then we've got y squared minus 1. So I've essentially eliminated now the parameter t and got a Cartesian equation that is in terms of x and y. And again, we could go ahead and either make, we have got x as subject, or we could look to express y in terms of x. So all I've done is simply thought, well, y is cos t. I know that one of the ways I can write cos 2t is 2 cos squared t minus 1. I've subbed that in and gone ahead now and eliminated t. Let's now look at solving an equation. So that was now a bit of work with parametrics, which we'll come on to later. Let's say I was asked to solve an equation. Let's say I had now sine 2a plus now cos a is equal to 0, and we wanted now solutions for a, and we'll take a between 0 and 2 pi. So let's go ahead now and look at solving for this. Now I've got sine 2a and cos a. I say to myself, I want this now, and I want to change this. I don't know how to solve this at the moment, but what I could do is change one of these. Now we know that sine of 2a can be written as 2 sine a cos a plus the cos a will be equal to 0. And now I have a common factor of cos a, which I can factor out. So I've got cos a, and that leaves me now 2 sine a plus 1 is equal to 0. So if we think now cos a is equal to 0, so we're interested in this now between 0 and 2 pi. So if we think now the cosine curve, we'll do the cosine curve. If we've got now cosine a is equal to 0, then we've got now pi by 2, which is just here, and then we've got 3 pi by 2, which is just there. So there's one of our solutions where cos theta is equal, cos a, I should say, cos a is equal to 0. Therefore, a is going to be equal now to this point right here, which is going to be pi by 2, and then by symmetry, pi by 2 back from 2 pi, which is 3 pi by 2. So a is going to be equal to pi by 2 radians and 3 pi by 2. Okay, let's deal with this one. 2 sine a plus 1 is equal to 0. So sine a is going to be equal to minus 1/2. And again, we can see now if we have the sine curve, let's go ahead and just chop that down. You might do these with your known values, or you might do them on a calculator. Let's just do that. So what we're going to have is something looking like so. So we're interested in this between 0 and 2 pi. So we'll have 1 just here. This now is going to give me pi, will be at 7 pi by 6, and then will be now 11 pi by 6. So if you do want to check those, we're just simply now looking at this using our known angles. If you want, you can find principal value. Principal value, we're going to end up now with the minus, and this will give me now the minus pi by 6, and then by symmetry we'll have one back here as well. So all we're doing is adding multiples on. So we can say that a is going to be equal to 7 pi by 6, and then we're going to have 11 pi by 6. If you want to check them in a calculator, you can go ahead and do that. So that's solving an equation using now the double angle identity. Okay, let's do another one. Let's say we had, for example, now tan 2 theta. So let's write this out. Say we got tan 2 theta multiplied by tan theta. So tan 2 theta is equal to 2. A few different ways around doing this. If we say now, let's just take theta, nice straightforward interval. Let's say we've got now theta is going to be between, we'll go from 0 to 360. So we're working degrees on this one. Okay, so what we could do is write this now as 2 tan theta over now 1 minus tan squared theta. That now is tan of 2 theta multiplied now by tan theta, and that's going to be equal to 2. So what we can see now, I've got here 2 tan squared theta, and then multiplying by the denominator, we're going to have 2 tan squared theta will be equal to 2 lots of 1 minus tan squared theta. So all I'm doing is multiplying the numerators, which are going to give me that, and then we've got now multiplying through by the denominator, we've got 2 lots of 1 minus tan squared theta. So the 2's can cancel. So we can see now, adding the tan squared theta to both sides, we've got 2 tan squared theta will be equal to 1. So we can say tan theta will be equal to plus or minus the square root of 1/2, which is going to give us 1 over root 2. So we would solve now for tan theta is equal now to 1 over root 2 in the interval where theta is between 0 and 360. And then when tan, so let's put this on, tan theta is equal to minus 1 over root 2. So if we wanted to do that, let's go ahead, theta, in our calculator, check we're in degree shift mode 3. Let's now do the inverse tan, and we'll now have 1 over, let's do 1 over root 2, and that's going to give us now 35.3, I'll do this to 1 decimal place, 35.3 degrees, and then we're simply going to be adding now multiples of 180. We know the tan curve cycles every 180, so if I add 180, what's that going to give me? 215.3 degrees, and then the next one will be outside the interval. And we can see if we look now, if we'd made this minus, we'd end up simply with now the negative result. So let's put that in. we'd end up with minus the 35. We would add now the 180, and then that would give us now 144, and then if we added another 180, so let's just put that on 144.7, so we've got now theta is equal to 144.7 degrees, and then if we add the next 180, we can see now that that's going to end up giving us the 324.7. So 324.7 degrees. So that's just using now the double angle identity, and that's one way of doing it. It's up to you at this point how you want to solve your equations. I've kind of breezed through that a little, but hopefully this stage now has shown you how you could solve for those. And again, if you wanted to check, you could simply plug them back in to find those values. So there's a brief introduction to the double angle identities. So we've got sine of 2a, cos of 2a, and tan of 2a. What we're now going to do is look at the half angle identities. And the half angle identities simply come from the double angle identities. Often students get confused about these, but essentially it's just the double angle identities in use. So let's say now we've got sine of 2a, we've got cos of 2a, and then we've got now the tan of 2a. We've seen all of these. This is now 2 sine a cos a, this is cos squared a minus sine squared a, or 2 cos squared a minus 1, or 1 minus 2 sine squared a, and this is just 2 tan a over 1 minus tan squared a. What we're going to do in this particular case for the half angles, and I'll just write them here, these are the half angle identities. We're going to let now, and just put them here, we're going to let 2a be equal now to, in fact, let's just start off with a. Let's start off now with a, and we'll let a be equal to theta over 2. So let's start off with a being equal to theta over 2. So if I sub this in now, all we'll have for sine of 2a, we'll have the sine of 2 lots of theta over 2, which is going to be sine of theta, and this will give me 2 sine of theta over 2 cos of theta over 2. So we're simply now replacing a with theta over 2, and this is a really important result. So we can get the sine of theta can be expressed as 2 sine of theta over 2 cos of theta over 2. So if we look now at cos of 2a, when a is theta over 2, we can say that cos theta is either equal to cos squared theta over 2 minus sine squared theta over 2, or we could say it's 2 cos squared theta over 2 minus 1, or 1 minus 2 sine squared theta over 2. And again, these are really important results, especially when we come on to work with calculus. So let's put those in. And then quite clearly we can see that tan theta, so tan theta is going to be equal to 2 tan of theta over 2 over now 1 minus tan squared theta over 2. So this now is for half angle identities. And in terms of work with them, there's no real difference when we're looking at these in terms of a double angle. Just see them as double angles, but just split now a into theta over 2. So let's go ahead now and solve an equation. Let's say we've got an equation, and we'll look at an equation using the half angle identity. Say we've got now, let's say we've got that 6 sine theta is equal to, let's go for sine of theta over 2. So we wanted to solve this. Let's say now that theta was going to be equal, let's say theta was being between 0 and 180. So let's go ahead and get some solutions for this. Now I'm looking at this and I've got theta over 2. But what I could do with sine of theta is write this as 6 lots now of 2 sine of theta over 2 cos of theta over 2. So all I've done here is written now the half angle identity for sine of theta, and that's going to be equal to sine of theta over 2. So I've got now 12 sine of theta over 2 cos of theta over 2, and then minus sine of theta over 2 will be equal to 0. Now if I'm interested in theta between 0 and 180, I'm interested now in theta over 2 between 0 and 90 degrees. And this is one way that you could look at it, because essentially we're going to double up our answers. So let's take the common factor of sine of theta over 2 out. That's going to leave me 12 cosine of theta over 2 minus 1, and that's equal to 0. So from here we can see that the sine of theta over 2 will be equal to 0. So if we look at this now, we're interested in this 4, and we're going from now, if it's theta over 2, we're 0 to 90. So what we could say then is at this stage that theta over 2 would be equal now to 0, and then of course we're going to have our next one, which is 180, which is going to be outside the interval. So we can say from there that theta is going to be equal to 0. So that's that one done. So I'm just looking now, if we're solving this equation, consider the sine curve. We've got 0, 180 and 360. So in terms of this interval right here, we've gone up to 90. The other one now is that cos of theta over 2 will be equal to now 112. So we've got cos of theta cos of theta over 2 is going to be equal to 112. So we could say now, let's move this here, and we could say that theta over 2 is equal to the inverse cosine now of 1 over 12. And all we need to do is solve this for a principal value and then consider by symmetry the next values. So if we look at this here, we're going to be interested in this between 0 and 90, which is going to give us, let's just put this in a calculator. So what we'll do then, we're in degrees mode, shift cos now of 1 divided by 12, so 1/12. So let's do that. What do we get? We get theta over 2 is 85.21, so let's write this out. So theta over 2 is going to be 85 what did we have? 85.2, let's put 85.2. Now if we consider by symmetry, what the next one we'd have is going to be 360 back from this. Therefore now we've got no other solution in this interval that we're interested in. So all we would do now is multiply both sides by 2. So if we just times this now by 2, that's going to give me 170.4. So we've got 170.4 degrees. So these are our solutions. We've got now 0 and we got 170.4. So we've gone ahead and used now the half angle identity to solve for this particular equation here by switching it up. So there we go, there's some work with the half angle identities. As you can probably now see, the double angle identities and the half angle identities are essentially very similar. Well, they're related. So if you come back to where we were proving identities right here, and then we were looking at finding the values, you can use the half angle identity to prove such results. In a later video, I'll look at some typical exam questions that go through the double and half angle identities, but for now, hopefully that's given you a good introduction. So from our addition formulae, or the compound angle identities, where we've got sine of a plus or minus b, we've taken now b to be equal to a and express this now as sine of 2a, and the same for cosine and tan.